Alright, so I know we have some folks that are either out of town or ill, and I just wanted to put some of these things into a video to make sure that everything is a little bit more clear, because Le Chatelier is definitely a principle that's easy to kind of have some simple mistakes on. So I wanted to check about a video in case there were any to try and make it a little clearer. So we do know so far that for equilibrium it has to occur in a closed system. And that it's the point at which the rate of the forward reaction and the rate of the reverse reaction are the same. However, that doesn't mean that we have the same amount of reactant and product. We can have, 2/3 to 1/3 or 3/4 to 1/4 or, quite a significant difference in amount. And so Le Chatelier, from Monday, we know that there are 3 things we can change. And that's the main thing coming away from Monday that I was hoping that folks have. We can change 3 things, and those 3 things are temperature, concentration, or pressure to shift a reaction. So when we look at this equation here, and we want to be able to answer questions like we have here for number 3, let's talk about each of the 3 things that we can shift. Okay, so we can shift concentration, and before you write maybe anything, or at least when you write this change in concentration, make sure you write this reaction shift away from an increase and towards a decrease part, because that's true for every example. Okay, so reaction shift away from an increase and towards a decrease will always be true. If we look at this reaction then, when we go from left to right, which is the exothermic direction where we're producing heat, we've got nitrogen gas and hydrogen gas producing NH3. And so when we go this way, we're producing NH3 and heat, and when we're going this way, we're producing nitrogen gas and hydrogen gas. So let's try seeing what would happen. If we increase the amount of either or both of those reactants, it's going to shift away to the right. It's going to start to produce more product. That kind of makes sense, because if we have more of the molecules, they're going to run into each other more frequently, and it's going to probably help this forward reaction to happen. Same thing if we have more of this, if we increase the amount of this, it will shift it back, and we're going to end up having more of the gas form. Okay, so we can shift it forward, we can shift it backwards, and with an increase, just depending if we have the increase on this side or the increase on this side. Our other option, of course, is to decrease. So if we start to lose some of this gas or pull that out, or in some way make it react with something else, when we do that, we're going to actually end up with it shifting in this direction. If you think of like a teeter-totter, and we have, I was going to say the recording that I've done where I can show pictures on the side isn't working, so I'm sorry about that I just have to kind of draw with the cursor, but that's the best I've got right now, unfortunately. New computer and it all changed. Is that if we have a teeter-totter and equilibrium, it's horizontal and straight, decreasing the amount is kind of like letting this side go up, okay? And if this side goes up and we want to bring it back down, we have to shift weight over to this side to pull that back down. Another way to think about it is kind of like there's a hole that you're creating, and it's going to shift this way to fill the hole to try and keep it at equilibrium. All right. So changing concentration is fairly straightforward. If you increase, it moves away. If you decrease, it moves towards. And it turns out, same thing with heat, with temperature. We need to write the heat separate. We can also write energy or delta H here. There's several different notations that you could use. But what we want to see is that if we have the heat, if we increase the heat, again, just like with that first example, we're going to have an increase move away from the increase. So if we increase the heat, everything's going to start going faster, but especially this reaction going this way, right? Where the N2 and H2 are being created. Then if we decrease the heat, well, it's going to shift to the right. Okay, it's going to shift to the right. It's going to try and fill that heat hole in a way. Another way we can phrase this, however, if we think about it, the direction left to right is exothermic because it's producing heat. The direction right to left is endothermic because that heat is being absorbed. So exothermic this way, endothermic this way. When we add heat to the system, it makes it shift this way, which is what we were saying there at the beginning. So when we add heat to the system, it helps to make the endothermic direction occur. And that is exactly what we talked about and touched on with Gibbs free energy. When we have that delta G equal to delta H minus T delta S, we increase temperature, we can help make a less favorable enthalpic reaction occur sometimes, because we can get a negative enough T delta S to cancel out a potentially positive delta H. So bringing the endothermic exothermic back into Gibbs free energy with a little bit of forward and backward movement there to touch on. The last one, pressure. So just like the other two, right, we're going to have a shift away from an increase and towards a decrease. That's coming from, the increase in movement that's generally happening in these scenarios. But an important thing for pressure is going to affect gases significantly more. If you remember our FET simulation from last semester that I'm going to pull up in a sec, we know that changing the volume of a container can actually start to make the pressure and temperature increase as those molecules are hitting the sides faster and with a little bit more force. Let me pull that simulation up for you all so you can see it. So we can see that when we have, in this simulation where we have water as a gas, we can see that the pressure, as we increase the pressure, already we can see these are starting to run into each other a little bit more. We're increasing the pressure by decreasing the volume of the container because gases fill all the space possible. As we increase this pressure, they're going to start moving faster and faster and faster. And that's going to increase the chances that they're going to run into each other and form a new bond. It increases their speed as they're moving around. So all of those can kind of contribute to new bonds forming a little bit faster. So I just want to point out gases are affected by pressure much faster than solids because really with pressure what's happening generally is we're frequently changing the volume of our container and when we do that, that's going to affect the gas a lot because they fill the containers as much as possible. So it's kind of a trick question that might come up sometimes is that, they'll give you gas, liquid, gas, and it's like, well, it's not going to really affect it because they all have to be gases. So for pressure, the only thing that is additional or different is that we have to take a step real quick and look at how much gas is on either side. We know that all gases occupy the same amount of space because 1 mole is defined as 22.4 liters of any gas. And so this is 1 mole of gas, that's 22.4 liters, and this is 3 moles of gas, so that's 22.4 times 3. We add that together, we end up with 4 moles of gas, so that's going to be, 88 point, like math, trying to do it in my head, around almost 90 moles of gas. We're going to round to the tens there. And then here we've got 2 moles of gas, so this is going to be, about 45 moles of gas, and essentially 45 liters of gas. Over here we have 4, so 1 plus 3 is 4 moles of gas on this side. Over here we have 2 moles of gas on this side. Obviously we have more gas on this side. So if we look at this drawing, or this simulation that we had going, if you imagine you have 2 different ones of these, and I think we can add more gas, if I add more molecules, what's going to happen is that having more molecules, when we increase that pressure, it's going to affect it faster. We've already got like 8, 10 that are running into each other a lot faster. Now they're all almost seem to be kind of having some effect from that pressure. Whereas having fewer moles of material in there are going to make them, it's not going to affect it as fast. So whichever side has more whichever side has more is going to feel the effect first. So an increase causes a movement away from that side because it's just like increasing amount, right? If we increase the amount, it would shift to this side. If we increase the pressure, because this is 4 mold, it's going to move that way as well. And if we decrease, it's going to come back and try and fill that hole. So those are the possible permutations with Le Chatelier's principle, and our goal Monday and today with the lab that if you're absent you don't have to do, but the homework that was given out Monday you do need to do, is that we want to be able to see how an equilibrium point is going to shift based off of having these changes in pressure, temperature, concentration. Here are some more practice problems, and the slideshow does have the answers in the speaker notes, so you can check that you're getting them right. Hope you all are doing well. Thanks for checking in.